organizers and for giving opportunities for pre-visit to KAIST. Okay, the work I'm going to present today is about the mass-critical generalized KdV equation. So we can understand the generalized KdV equation is as an example of the nonlinear dispersive equation. So the technique developed for another example of the nonlinear dispersive equation, like the linear Schrödinger equation or linear wave equation, is successfully used for the KdV equation too. So, but recently there are big progress that was made for the nonlinear Schrödinger equation or wave equation when the nonlinear power is mass critical or energy critical. So they studied the global theory for such an equation. So, but the purpose of this work is to investigate how their argument, which is called the concentration compactness, can be applied to the low dimension, the KdV equations. Okay. So, in collaboration with the Rowan Theorem and Shang-Li Chao and Monica Bijan, we got kind of partial and the conditional result about the scattering problem of the generalized mass critical generalized KdV equation. So the generalized KdV equation reads as following. So the linear part is the third order in space dimension, and then it is defined on the one space dimension and the real value, and it contains a nonlinear term, the power type nonlinear term with one derivative. And then the sign of the nonlinear term could be the plus or minus. So usual the KdV equation is the case when p is 2, which means the nonlinear term is a quadratic. And then when the p is 3, then it is called the modified KdV equations. So those two KdV equations has the physical model from like a water wave theory or some the plasma physics or something. But the equation they're under investigation today is when p is 5. That is called the mass critical generalized KdV equation. Those generalized KdV equation enjoy the two conservation law. Mass L2 norm is conserved, and then also energy is conserved. Okay. So those two, the conservation law, mass or energy, they are the most common, the conservation law to the most the canonical, the dispersive equation. But when p is 2 or 3, which means the KdV or modified KdV equation, they have a very special structure. So actually, the Bruce discussed just before. In that case, it is the completely integrable, so it enjoys the infinitely many, the higher order, the conservation. But in this case, in our problem, it enjoy only two conservation law. And if you look at the energy, when mu is positive, it's plus 1, and then p plus 1 is even number, then energy is positive definite. So in order to control the H1 norm, by the energy conservation law, because this is both terms are positive, so the H1 norm is automatically controlled once they define. But otherwise, so which means mu is negative and p plus 1 is an odd number, then the energy is indefinite. So it could be, even if the energy conserved, both terms go to the infinity. And such an equation also enjoy the lateral symmetry. And one is obviously the time, the spatial translation and time translation, and also with scaling. Okay. So when you say the u lambda is the scaled the solution, then when p is 5, the mass of the scaled solution, the mass of u lambda is same as the mass of u. So that's why we refer that when p is 5 case is mass critical. And when p is 2 or 3 or 4, then it is referred as a mass subcritical. And then because this is one dimension, but however P is big, there is no energy critical case. Okay, and then so just for further energy, let me explain that. I explained that when U is -1 and then P is the even number, then energy is indefinite. In that case, it is called the focusing, which means the linear part, which is an early equation that pushes the solution to disperse, to spread out. But the role of the nonlinear term is attractive, so pushes the solution to the center. So that there is a kind of the balance of the example, the balance of the solution, which means so the one of the easiest example is the Solitone solution. So just plugging in the solution in this form, so which means keeping each shape, the shape is constant and it is just propagating like a traveling wave. Then it reduced the original equation reduced to just one ODE with in one dimension. It is just ODE with asymptotic boundary condition. Then in 1D case, we have the explicit formula for the ODE. And then by the scaling symmetry, we can find out the traveling solution, Solitone solution for arbitrary speed C. Okay. So this Solitone solution, the crucial the fact about the Solitone solution is a non-dispersing object. So usually without the linear term, every linear solution should disperse, which means at infinity norm of the solution that should decay to the zero as it equals to infinity. But if you look at this solution, it is just to travel without changing its shape, so it is non-dispersing object. And if you compute the mass of the scale, rescale the solitone, then you're going to have such a power. Look at the exponent, you can see the 5 minus p vector. So when p is 5, then you don't see this. So which means the mass of by the scaling symmetry, the mass of the rescaled solution are all the same. So there is only one. It could be rescaled, but the mass of all rescaled solitone are the same. Okay? But when P is 2 or 3 or 4, then there could be arbitrary small mass solitone. So by choosing C to be small. So usually in the subcritical generalized KdV equations, then the small solitone moves slow, but fast solitone it has a big mass. But in mass critical case, all the solitone with any scale has the same mass. So because the solitone solution is one of the simple non-dispersing objects, so we can think we can expect that that the solitone is a minimum. The perspective minimum mass is non-dispersing object, which means if the initial data of the mass is less than that mass, unit mass, then the mass is too small to form the non-dispersing object. Okay? So we revisit this algebra. And when mu is 1, the mu is 1 and P is 3 or 5. So in our case, then there is no Solitone solution. Okay? So it is referred as a defocusing case. So in this case, the role of the nonlinear feedback is also pushing. Right? So pushing the solution to the outside. So from the effect of the linear part and nonlinear part, it is the same. So we can expect that the solution is at infinity norm of the solution is became to zero, right? Okay, then so we are not considering the classical solution. That we are considering some sort of the weak sense of the solution. But here we are going to call it a strong solution, and then so we explain what kind of solution we're looking at. First of all, for the linear problem, by taking Fourier transformation and then solving the ODE in Fourier side, and then we have a very good expression of the linear solution. Okay, and then we're going to denote that the linear solution, linear operator for given initial data is in view of the Fourier, each Fourier multiplier is e to the I, e to the negative t, and then with 3 derivatives. That is a notation of the linear propagator. And then by the two-hammer formula, we can change the differential equation into the integral equation. So the solution that we are looking for the linear problem is a function the L2 in space and then the continuous in time, and the satisfying these different integral equations. Okay, so when you work on the local well-hypotenuse or well-hypotenuse, we are seeing this such a function. Okay, so local well-hypotenuse theory is well established about 17 years ago by the Koenig-Ponce-Vega. And then the main ingredient of the local theory, local well-hypotenuse, is called the smoothing estimate. So usually in the dispersive equation, like a linear wave equation or Schrödinger equation, the strict-party estimate play a crucial role for the well-hypotenuse. But the strict-party estimate, they still have the strict-party estimate for the KdV, but it doesn't have, because we have in the nonlinear Schrödinger or wave equation, there is no derivative on the nonlinear term. So when you try to solve the problem by the Picard iteration, they don't need some sort of smoothing effect. But for the KdV equation, because we have a derivative, we need some sort of smoothing, right? So we have to use a local smoothing estimate. So that is is written in this form, like because of the first term that we usually call this whole estimate local smoothing. So you can see the one derivative of u, when u is a linear solution, linear solution for this inhomogeneous problem, then when you localize in x, so localize in x, when after you integrate in time, then you will see some smoothing effect, right? So actually, that kind of the properties observed by the Toshio Kao for about 30 years ago. So when you localize in space, this is the space dimension, and then this is time dimension. Okay. Then the crucial property of the dispersive equation, when we have the initial data, then it may consist of the high frequency data and the low frequency data. Okay. Then from the solution to the linear equation, high frequency data is moving much faster, but the low frequency data is moving slow. So actually, if you just plug in the planar wave to the area equation, then the solution is looking like that. So the phase velocity of the planar wave is negative c squared. So if c is big, then the high frequency phase is moving faster. So if you localize in space, then high frequency, this is a time variable. High frequency data is moving much faster, but low frequency data is moving slow. So the time, the staying on the fixed space interval is quite different. So the high frequency data staying very short time, but low frequency data is staying the long time. So it gives us a damping for the high frequency, the coefficient. So that is that can be reinterpreted as the smoothing effect. So we have the smoothing effect only. We don't have a global smoothing. We have a smoothing effect only when it localized in space. And the second estimate is another form of the Strickhardt estimate, but we integrate in time first. So the proof of this is very similar to the proof of the Strickhardt estimate, but in the one space dimension, we can, because space dimension is 1 and time dimension is 1, we can switch the role of the space and time, and then applying the same argument, we can obtain such an estimate. And then those two estimates is obtained by interpolating those two. So this first and second one is an endpoint estimate of the local smoothing. So we are going to call everything is a local smoothing estimate. And then for the nonlinear term, you will see the L1 and L2 norm is a dual norm of this. So this is a dual estimate. So when the nonlinear term has one derivative, its derivative is also recovered in dual estimate. Okay. So for the mass critical case, when U is when P is 5, then actually we are going to iterate. We are going to use a Picard iteration to obtain the local resistance and on the L5, L10 node. L5 in space, L10 in time. So simply it is because of for the dual formula, if you just apply that estimate, then we have with the previous F is U to the 5. U to the 5 is in L1 and L2. So by using simply hold up, this is bounded by L5, L10. Okay. So we can iterate in that space. But for the local resistance, so something that should be small. So especially for the linear solution of the L5, L10 norm, that is supposed to be small. So we can iterate. We can use a contraction principle on the time interval of the linear solution of L5, L10 norm of the short time interval when this is small. Okay. When so by reducing the time interval, that we can make it small, because for whole time interval this is finite. So we have the local solution on the time interval is satisfying such a condition. So the time interval for the local resistance doesn't depend not only on the norm of the initial data. It depends on profile of the initial data. So the mass conservation law doesn't imply the global existence. Mass conservation cannot be combined with the local theory to obtain the global existence. Okay. And there are some other the application of the local theory, the local smoothing estimate, and the same iteration argument. So one of them is the small data global existence and the scattering. Let me explain what the scattering is later. So initially, if the mass of the initial data is sufficiently small, then we don't have to reduce in time. So we reduce the time interval. For whole time interval, we can iterate. Then we don't have a linear solution by the iteration on whole time interval. Okay. And most generally, we have the stability. So which means we can perturb the equation by adding some sort of small inhomogeneous fact, and then we can perturb the initial data. Then so if E is a small insurable sense like this, So it's a negative derivative with in dual norm is small. And then if the initial data is close to the original initial data, then the solution, and the assumption is that there is approximate solution to such an approximate problem with the approximated initial data. Then by the similar argument, we have a genius solution without this, and then by using the initial data, genius solution to the KdV, to GKdV, and the genius solution is close to the approximate solution in alpha rectangle. Okay. So you can understand that the small data global existence or local existence is a corollary of this stability. Okay. So in our analysis, because we are going to use a lot of the approximate solutions, so we are going to use this stability theory over and over. Okay. And the local theory also imply something about the scattering. Actually, the scattering refers an asymptotic behavior of the solution. It is a kind of asymptotic behavior, but so in order to consider the asymptotic behavior, we're supposed to have a global solution, right? When you have a global solution, and heuristically we can think when you like the linear solution, when at infinity norm of the u decay to 0, then u to the 5 is going to 0 even faster. So in the equation you can observe that the nonlinear term, because this is going faster than the linear part, the linear term is much smaller than the linear part. So the nonlinear, as u go to 0, ut go to 0, the nonlinear term is getting negligible. So in that case, we can expect that the nonlinear solution almost solve the linear problem. So the nonlinear solution converges to some linear solution. Okay. So here, u plus or u minus is referred as the asymptotic state. So when t goes to the infinity, then the linear solution converges to some linear solution. And then one main property about this the scattering, because the linear solution at infinity norm of the linear solution converging to 0, the linear solution also by this convergence converging to also 0. So the Soliton solution, if it is just a travel without decay at infinity norm, then that is a very the simplistic counterexample of the scattering. Okay. So once you have a Soliton, there is no scattering. Okay. Then, so this is a qualitative the definition of the scattering. And then by using the local theory, we can change such a qualitative property of the scattering into the quantitative statement. Okay. So by using the local theory for given the asymptotic state, under assumption that we have a global existence. Once we have a global solution, and then for given asymptotic state, we can find out the linear solution converging to the given asymptotic state. Okay? It is the one local one application of the local existence, but we're gonna do iteration over the time interval from capital T to the infinity. Actually, we can understand asymptotic state is kind of data at time infinity. Okay? And then, so for given asymptotic state, for sufficiently large time, we can use a local theory because the linear solution of the iteration norm is small. And then once you find out from asymptotic state, you're going to find out u of t. And then by the global existence, we can find out the initial data for any time. Okay? And so so this is one the result of the local theory, and then from the local theory we can also obtain the boundedness of the space-time norm for the linear solution. For the linear solution, that we already have it, right? But for the linear solution, once you find such a boundedness, then that implies the scattering. Okay, that is also the application of the linear, the local existence in the same form. Okay, and assuming that global existence, and then so the second property is sometimes called the asymptotic completeness, and then the first the property is called the existence of the wave operator, because the wave operator is an operator from asymptotic state to the linear solution. Okay, so if both are true, then we're going to call it is the scattering is whole true. Okay, then the thirdly, once we know the global existence, then by using the local theory, we can see that the asymptotic completeness is equivalent to the boundedness of the space-time norm. So which means the convergence as time goes to infinity, is equivalent to the quantitative the statement like boundedness of the space-time norm. Okay. So from now, when we consider the scattering problem, we are looking at only the quantitative the statement. So the effort will be made to find out to show that the boundedness of the space-time norm, the L5 L10, is bounded by some constant depending on only mass. Okay, then let me review some well-known result and then they presented the conjecture for the global existence and the scattering. For the regular initial data, when the initial data is in H1 norm, then in the focusing case, when the equation allow solid solutions, then I'm sorry. When mu is 1, when defocusing case, so when we don't have any when you don't have any the solid solution and energy is the positive definite, then if the user is in the H1, then by the energy conservation is immediately implied that the global existence. So because energy is positive definite and it is conserved all the time. But soliton and energy is positive, the energy is indefinite, then we still have a global existence for the small mass, if mass is smaller than mass of Q. So it is because by the sharp calculated Nirenberg inequality, so here the sharp means a sharp constant. So actually the calculated Nirenberg inequality is known before the Weinstein period, but the Weinstein they observed that actually the minimizer of the calculated Nirenberg inequality is attained when U is Q. So the minimizing constant, which means a sharp constant of the calculated Nirenberg inequality is written as a function of Q. So L2 norm of the Q. Okay. So from this inequality, if we plug in it into the energy conservation law, then actually the P plus 1 is 6. So basically the second term, by the inequality, it is replaced by the H1 dot and then L2 norm. And then if the mass, so energy is conserved all the time. And this this is less than that by the random inequality, so this is greater than, with the negative sign, then this is greater than like some constant times.
Marshall, can you turn on the lights? Please. No. To the left of the door. To the left of the door.
Some constant times mass of U square. So if in this form, if mass of U less than mass of the C, then this constant is positive. So because this is less than 1. So by the energy conservation at the actual norm cannot go to the equilibrium. Okay? But if mass is the same or greater than the Q, then this constant. So this the energy conservation law is useless to get the global existence. Okay. So so now let me prepare to state the scattering conjecture for the KdV equation. First of all, let me define the scattering size. So which means, so if the initial data is less than L, then we're going to have the scattering. Okay, and then we're going to choose the supremum of such a number, such a positive number, to satisfy this condition. Which means, so that is called MC, there's a critical mass. So which means if mass of the initial data is less than critical mass, then we have scattering. Okay. Then by the small data scattering theory, because from the small data theory in the local theory, so the critical mass is strictly greater than 0. So if mass is just smaller than epsilon, then we have scattering and global existence. And in focusing case, if the equation admit the Soliton solutions, then critical mass should be less than or equal to MQ, because Soliton solution is a counterexample of the scattering. Okay, so we can expect that if mass from this observation that we can expect that at most the scattering size is MQ. And then for the subcritical case, because we don't have the soliton and then we don't have counterexample, so and by the heuristic argument we can observe that the U is the infinity norm of U that could go to the 0, like a linear solution. So we might have the scattering. Okay? So we can expect that the scattering in defocus case, we can expect the scattering for arbitrary initial data. Okay, but in focusing case, our conjecture is MC is the same as MQ, so which means we already know that MC is less than or equal to MQ, but the conjecture is saying that MC is the same as MQ, which means the soliton is actually the minimal object of minimal non-dispersing object. So if the mass is less than the soliton, then it should scatter. Okay, but so we can make a conjecture. There's such a conjecture for the mass critical case, but the subcritical focusing case, even if we have soliton, we cannot make such a conjecture because you remember that rescaled soliton for the subcritical case is C to the sum alpha, and then if you choose C small, then the mass could be very small. So we have an arbitrary small non-dispersing object in subcritical case, so we don't have such a conjecture for subcritical non-focusing case. Subcritical focusing cases. Okay. This is a main difference from the nonlinear Schrödinger or the wave or Klein-Gordon equations. Okay. Okay, so this is a conjecture for the generalized KdV equations. It consists of the two pieces, focusing or defocusing case. And so our main theorem is to give us some connection to the scattering conjecture of the Nonlinear equation and the critical generalized KdV equation. So I mean, to prepare for the work for the Nonlinear equation. This is the 1D mass critical Nonlinear equation. This is also mass critical. This enjoys also scaling symmetry, but by the scaling symmetry, the mass of rescaled solution is preserved. So that is also mass critical. And Nonlinear term doesn't have any delivery, but it is also printed as like the KdV equation. So the theory for local theory for the 1D, the Nonlinear equation is quite parallel to the KdV case, but here we have to use the Strickart display. So the symmetric Strickart norm, the L6 norm, when if this is bounded, then that implies the scattering by the same time. Okay, and so in this case we have a soliton solution, and the Q is the same function. Okay, then so we still have the same conjecture for the 1D NLS. So defocusing case, the critical mass is infinite, so which means the scattering holds true for any data, and the focusing case, scattering holds true when the data is less than the mass of the data less than mass of the soliton. Okay? And there is the theorem, the connecting two scattering conjecture 1D NLS, and or the mass critical generalized KdV, because the both scattering problem are far from the conclusion because of some reason. So in 2006, what Tao shows is the scattering conjecture for generalized KdV is stronger than scattering conjecture for the NLS. So once they have a scattering for GKdV, then we have scattering of NLS. So that is just connection, but that doesn't solve neither of the problem, but it gives us a connection. The idea of such a proof is kind of a simulation of the KdV solution by using the Schrödinger solution. Okay, so let me work with the linear case first. In the linear case, if you solve L equation, the linear KdV equation, then in the free side it is written as in this formula. Then we're gonna change the variable. The frequency C is a very large frequency and around some rescaled frequency, the eta over some big number. Then we're gonna expand. We can find just a Taylor expansion of the phase function, the cubic function. And then if we rewrite that, you will see the phase function is written in this form. So if you just ignore the third term, then you can observe that actually that the frequency integral form is written as the solution, linear solution to the second order problem, because this is eta t I t eta square, and then the I eta times something. But it is evaluating at this point at x plus 3t n square over the square root of the 3n. Okay? But when the u now is compactly supported, the Schwarz function is decaying faster, then we can ignore this, because if n is big, then this term is much small, very small. So approximately we can observe that for given the linear solution for the Schrödinger equation, we can find approximate solution at very large frequency n. So which means at large frequency, at very high frequency, the linear wave for the Schrödinger equation and KdV equation take similar. They have some sort of connection. Under some sort of scale, Schrödinger scale. Okay. So this is how we create the approximate solution to the KdV to the area equation, the linear equation. But when you have a linear term for the linear Schrödinger equation and the linear term for the equation, so we have to the match. We have to look at the coefficients of this, and then by working out that we can find out such a right the coefficient of such a solution in the linear case. So we're gonna have the by the computation we can claiming that this is a approximate solution. For given the Schrödinger solution, we can find the approximate solution at very high frequency. Okay? By using this such an argument, so we can show that some statement we can connect the 1D and the analysis scattering and then KdV scattering. So in order to show its conclusion, the conjecture of analysis, our goal is to show so when U is an analysis solution and L6 norm is bounded. Okay. Then initially the U, the linear solution for the analysis is given. Then we're gonna pull mass of U is like a big 1. Okay. Then for given linear solution, we have the initial data. Then by such approximation, we can find out approximate solution to the KdV like this. Then here we can also observe that mass of UN is also same as equal 1. So and then here the bigger 1 doesn't which is independent of capital N, so we can really choose the large the frequency data. And then so by using the scattering conjecture for the KdV, so we can find out this is L5 norm and then L10 norm is also bigger. So scattering conjecture of this is bounded by some constant times of the mass. Okay? And then so by the rescaling back, so we can connect the norm of this. Okay. So first of all, because this is approximate solution, by using some sort of the stability argument, we can find out the genius solution, and the genius the same norm of the genius solution is also of same comparable size, and then rescaling back, so at 6 norm of the solution is also similar the same size. So that's how we proceed. But in this approximation, we have to assume that we have to work on complex time intervals. So yeah, so that poses one difficulty in our analysis. Okay. So now we are ready to state our main theorem. So our main theorem is in view of the partial converse of the Tau's result. We're going to assume that the scattering the conjecture for the 1D Schrödinger equations, and then if the scattering for the generalized KdV is not true, then we have a minimal element. Okay. So it is kind of a compactness result. So once you have once you have a failure of the scattering, then there is an MC, and then MC for the defocusing case, MC could be finite. finite or focusing phase, MC could be like M of Q. Okay, if the scattering phase. Okay, then there exists a minimal mass whose the mass is the same as the critical mass, and then it is blocked in the sense that the space-time norm is going to infinity. Okay, moreover, such a minimal element enjoy some sort of the compactness, the property which is called almost periodic modular symmetry. So after by the symmetry, so the minimal element is localized in space and both localized in frequency space. Okay. And that statement is equivalent to that U of t. U of t is a solution for when U is in I. U of t is in a rescaled version of the U of t is in a compact subset of L2. Okay. So actually those two statements are equivalent in view of the generalized KdV theorem. So basically, this is kind of the first step toward to the scattering problem. So once you have by the contradiction, once you have such a minimal element, because minimal element should satisfy such a strong condition, the periodic modular symmetry, then so by working out such a symmetry, the strong property that we can show that it reaches to the contradiction. So there is one further step after the almost periodic modular symmetry. In this quantitative form of the almost periodic, we have a frequency scale function, and we have the position function. Then we have some sort of conditions, some sort of scenario about the frequency scale function. Frequency scale function could be, this is 1, not 0. Frequency scale function is just constantly 1, which means if you look at only the special case, it is localized in space with this. So this is called the solito-like solution, and or the frequency, the scale function goes to 0 when t goes to negative infinity or positive infinity. Frequency scale function is from 0 to 0. Okay? So which means the frequency scale function, if the frequency scale function is from some positive number to 0, then that implies that some sort of high frequency, the data move to the low frequency. So here, from negative infinity in time to positive infinity in time, such a frequency cascade happened twice. So we're going to call this the double low high the frequency cascade. And the third scenario is a frequency scale. We take one over t, the cube root of the t. So especially for this case, because the frequency scale is blocked at time 0. So and then the solution, the lifetime maximum lifetime span solution just exists from 0 to infinity. So that block at t equals 0. Okay, so this is one of the finite time block case. Okay. So actually the later I'm going to briefly give outline the proof of the existence of the minimal mass block solution, and then actually the second theorem is pretty standard. So it's in the sense that the argument for the second theorem is almost independent of the equation, so we can. So argument of this is automatically copied from some other equation like Schrödinger equations. Okay, so the idea to show some compactness, the problem is a concentration compactness. So that is related to the symmetry of the embedding. Okay, so we have the local smoothing is made like this, and then for the linear solution. But the problem is this embedding is not compact. So we can easily observe the counterexample of the compactness of the embedding. So counterexample are from just the scaling parameter, as the symmetry parameter. So for instance, if you look at the translation, then for such an embedding to be the compact, for given the sequence, so with the same mass, they suppose if this embedding were the compact, should contain convergence subsequence in L5 at 10 node. But if you consider just the translation, then because that is a translation, then it is converging to zero weakly. But whose they are the L5 L10 node or L2 node just preserved, which means they are not converging strongly in that sense. So the translating is one example. So, but such a linear equation that enjoys a lot of the great the symmetries, like a scaling symmetry and the time translation, spatial translation with what's that? Frequency modulation. All for non-compact symmetry responsible for the defect of the compactness of such an embedding. Okay? In that case, if it is just corrected their symmetry, the invariance, the parameter, then we might have some sort of weaker form of the compactness argument. So that is written as the profile decomposition. So for given the sequence UN, which is bounded sequence in L2X, but we don't expect by taking the subsequent we don't expect that this is converging to this has a convergent subsequent in L5 L10 node. But there exists the profile. This is the countable in many profiles, and then the parameter, scale the symmetry parameter. Then the UN can be written as a sum of profile, and then GJN is a symmetry. Okay, and then with the error, and then error should converge to zero. Error should go to zero. So in L5 and L10. Okay, and such a profile in such a profile composition, the good the property is the asymptotic orthogonality of the parameter. So one of four the symmetry parameter should take a part, which means the scaling parameter, if J and K are different, scaling parameter take a part, or the frequency modulation parameter take a part, or the time translation or time spatial translation and time translation. So by using such a asymptotic orthogonality parameter, we can, if J and K are different, then two profile, the product of the two profile eventually go to zero. So that's why we're going to refer this is the asymptotic orthogonality. And by using the asymptotic orthogonality, we can also obtain that the mass of this whole thing is actually the sum of mass of each profile. Okay. So by by using the profile decomposition, still though we don't have the compactness, but we don't have some sort of weaker form of the compactness. Okay. So let me give you the brief the outline of the proof. So so we're going to show that the existence of the minimal mass block solution. So that if the scattering conjecture is not true, then there exists the MC, right? And then by this definition, we can find out the sequence, schematic sequence of the solution with bound mass. Okay, and then M of UN is converging to MC, but they are all they are the space-time norm is going to infinity. And then we are going to show that this U of n is convergent, the modular symmetry, by taking subsequence it is convergent modular symmetry. Okay, and then we take the profile decomposition of the initial data for this sequence. Then, if it has if UN of 0 consists of only one profile, then it might be easier. But if it consists of the multiple profile, then we might have some sort of, we might not have the convergence. Okay, so we're going to consider the one profile case first. Then if it consists of only one profile, then the J is just one, so there should be J. And then the initial data is written in this form. But we are going to use the symmetry operation of the nonlinear solution. So far, for the linear solution, we have seen for symmetry, like a scaling, time translation, partial translation, frequency modulation. But at the beginning, I explained that there are three non-compact symmetry for the nonlinear solution, like time translations, partial translation, and scaling. But there is no frequency modulation symmetry. So that is the big issue in this argument. Okay, so because by using the symmetry operation of the nonlinear solution, we can recover the symmetry of the scaling and the spatial translation. Then after the inverse the symmetry operation, then we can change our our sequence of the initial data in this form. But in that case, Tn, which is a parameter of the time translation, and then frequency modulation could go to the infinity or bounded. If it is bounded by some argument, we can reduce to the case that is just 0. Okay? By changing the profile a little bit and then the error, observing the error to the error term. So we can reduce this. So we're going to consider 4 cases when the frequency modulation is 0 or infinity, and time Tn go to is 0 or infinity. Okay. So first of all, when the frequency modulation Cn is 0, then our solution when Cn is 0 and then Tn is 0, actually the sequence is written in this form, just the profile times some error. Right? So this is the form after the taking the symmetry operation. So actually, because this is just one profile and then something converging to 0, that is actually the minimal element. Okay, that is a claim of our main theorem. And then we need to show all other cases they reach to the contradiction. First of all, when Tn goes to infinity by using some sort of stability theory and the monotone convergence theorem and the linear theory, that we can reach it to the contradiction. Because the linear solution, because Tn goes to infinity, the time interval of space-time norm, at Tn to the infinity is getting smaller. So it's because Tn with the conversion to the infinity. So the norm of this should go to 0 for the linear solution, and by steadily decaying, the linear solution also goes to 0, which means the contradiction. The most important case is a case when the frequency modulation is going to the infinity. Okay? But in that case, we have to use the assumption of the scattering, the problem of the 1D NLS. By using the conjecture, when the frequency is very high, then from the same idea of the tau, so we can show such a theorem, such a lemma. So we begin from the initial data at time Tn, then by assimilating such initial data at time Tn, we can and then using the scattering conjecture for NLS, so we can show that there is the global solution for the satisfying this condition, and then with the finite needs of space and norm. Okay. So that, and then the following is the proof of this lemma. Okay. So in the proof, because the tau's argument only work when time interval is compact. So we're gonna divide the time interval into 3 pieces. So this is the middle time. In the middle time, for given for the linear solution, so we define the approximate solution to the KdV equation, and then for the larger time, larger in positive or in negative. Because in larger time, this NLS solution is well dispersed by the scattering conjecture for the NLS. So for the well dispersed solution, and then with a very high frequency, that is also well dispersed approximate solution to the generalized KdV. So we can just simply define the approximate solution as a linear solution. The simple. So actually, it contradicts with the minimality of the critical mass. So if we have a multi-profile, like a 2-profile, then eventually so this is like a linear solution, but they don't have any interaction. So by the asymptotic orthogonality. So these both are, sum of 2 is a linear solution, but if they don't have any interaction, then both are the approximately solution in itself. But the sum of mass is same as the minimum mass MC. Then mass of each profile should be strictly less than MC. Then by the definition of the MC, the critical mass, because this mass of each profile is less than critical mass, this should be the scatter, both are scattered. And then space-time norm of the both is sum of space-time norm of this, sum of 2, which is also finite. That's how we make a contradiction. But for such a purpose, we need to, in the profile decomposition, we need to define the approximate nonlinear solution. So for each profile, we're going to define nonlinear profile, beginning from this nonlinear profile at time 0. And then we can define approximate solution as a sum of the linear profile. And then by the minimality of the critical mass, we can reach into the contradiction. Okay. So that is the proof of the existence of the minimal mass of solution. And then showing the almost periodicity modular symmetry is pretty same as previous argument. So so we are going to show that the U of t is actually in compact set the of the A2, the equivalent, we're going to show that for any sequence Tn, so we're going to define this is a sequence of Un. Then we're going to show that by taking subsequence. So, and then this is conversion to modular symmetry. Okay? So we're going to repeat for this sequence of the initial of the nonlinear solution. We repeat exactly the same argument that we have to get the minimal element. Then we can have we can show that actually this is a conversion to modular symmetry. Okay. So that is the second main property modular almost periodic theory of the modular symmetry for the